Okay, so hello folks. So welcome to Cloud Native Live. So where we dive into the code behind Cloud Native. So I'm Mohammad Shahrir Al Musagim Mitul, and you can call me Mitul. And I'm a CNCF ambassador, and I'll be your host tonight. Okay, so every week we bring a new set of presenters to showcase how to work with Cloud Native technologies. Now they will break things, and they will build things, and they will answer your questions. So in today's session, I'm stoked to introduce Dimitri, who will be presenting on session on BellSoft's Java Part 2. And this is an official live stream of the CNCF, and as such is subject to the CNCF Code of Conduct. So please do not add anything to the chat or questions that would be in violation of the Code of Conduct. So basically, please be respectful of all of your fellow participants and presenters. So with that, I am going to hand it over to Dimitri and add him to the stage. Okay. So hello, Dimitri. How are you?
Hello, Matteo. Great.
Okay. So yeah, it would be very nice if you actually introduce yourself, and then I think we are good to go, right?
Sure. Let me share my screen. I'll just.
Okay.
All right. Um, this is actually the second part of this live stream. So for those who previously haven't seen the first part, here's the link. You'll probably also find the link in the description later. We are at the second part. So we still observe lots of Java images that I believe can help you to optimize your delivery to production, to optimize your deployments. My name is Dmitry Churko. I'm mostly focused on OpenJDK development, but overall focus of this development in OpenJDK is about making containers more efficient, bringing Java to developers, and to make it convenient for operations for everyone. And I worked at BellSoft, and BellSoft participates in great communities such as Linux, of course, the Cloud Native Computing Foundation, and also GraalVM and OpenJDK, which I will mention today. And we base our work on great open source projects such as Linux, such as OpenJDK and GraalVM, where we offer multiple interesting things. Our products with support. It's a distribution of OpenJDK called Liberica JDK, which I mostly covered in the first part. And also this Liberica Native Image Kit, the distribution of GraalVM, and Alpakita Linux. That's the basement, the platform to run those two in the cloud. So what's up with the native images and all the things? Last time we stopped at looking at build packs, which is a very convenient way to turn your Maven project or turn your Spring Boot application project into actually working container somewhere in the cloud. Let's check how we have what we were doing to run that container, to use it. It was like simply building this container using provided default commands provided by standard plugins. So you can directly use your Maven or Gradle project without or with some little additions to get a working container image right in your CI based on the work that developers have performed just to implement the application's business logic. So we created that container, right? I can repeat it, actually. And it's pretty fast. We just build an image. In this case, it's already a custom build pack. Let's check. It mentions BellSoft, right? So this is the configuration for the Git plugin, and this is the configuration for build packs. So in this process, we create that image. It's that simple. We have used Opakita and Liberica JDK in this process, and we can actually run this container, right? That we have just built the image. Now we can run it, and you see, yeah, there are some optimized parameters. I covered it in the first chapter, and we see that startup process, right? That CPU storm and CPU and memory storm. So after the application has started, we don't need CPU, right? We don't perform JIT compilations. We don't perform any initialization. And we don't even need as much memory before we get the actual load. And of course, when we get actual load, we will need, again, extra CPU, not just to perform the load, but also to perform some JIT compilations. And that it takes some resources, and that's a great startup problem. And you see it takes, well, some time to start the application. Could we just bypass it and start in a blink of an eye? Yes, we can do it. And it's also very simple. Yeah, let's look at the application again. Just to check that it really works. Yes. See, that's the homepage of the Spring Boot Pet Clinic example. So what we are going to change here in this approach, we're still going to use build packs, but we will add a parameter here. We'll say, please build a native image for me. So let's see how it works. Well, I must say in advance that it will take some time. It's a costly process, which will require a lot of operative memory. It will require some CPU to perform. But you see, we initially started with the same approach. We haven't configured a thing. We just passed the parameter. It can be configured as a property, and you can find some descriptions on our website how to start with native images for your Spring Boot application or your Maven or Gradle project. And you see now we download a different thing here inside this build pack. So we had nothing in our CI except some JDK installation to run that build system, right? And even that could be downloaded. And of course, some container engine, Docker in this example. And instead of downloading the regular typical JDK, we download something called VM Core, but it's a distribution of native image kit, which is downstream distribution of GraalVM. So we are going to create a native image. We are going to compile our Java project into a native Linux platform executable. And in this executable, we will have all that code of our application, not as bytecode, but it will be compiled into native platform code ahead of time. It will require this machine time only once during that initial compilation stage. It will require this step to be performed inside our continuous integration environment. Though it also means that we must reproduce the same hardware environment in our CI as the hardware environment that we are going to have in production. Because this is a compiler that works and that has some target for our instruction set, etc. So it can be more or less basic, like some universal x86 code, for example, but definitely not like trying to compile x86 on ARM and vice versa. And it's better to have all the CPU extension extensions available to you at the build time, being same CPU extensions as we are going to have in runtime. And you see, we are going to use a lot of memory. We are going to spend, well, some time, I would say 6 to 8 minutes for this not so large project. Meanwhile, we can look at some artifacts we are going to use here. So what's that native image kit? Yeah, we can find some information here in product section on the website. So you see it's called Liberica Native Image Kit. There are, of course, some articles. You can find some articles in our blogs, and you can, of course, download it here. Go to download center, right? There are different versions, and such versions are a combination of base JDK version, where we have, for example, JDK 17 or 21 LTS as a base, or the very latest at the time, JDK 22 as the base, and also a version of GraalVM that is put on top of that, which is 23, or the very latest 24, which is put on top of JDK 22. So it's a composite. We can also select platforms just with a regular JDK, and you can use this artifact as a JDK, actually. You can show it to your Maven build system, for example, and say, please compile the native executable. Don't create any containers, just compile it. It's also possible.
Dimitri, I think we have a question regarding this thing, like BellSoft's Java. So the question is from Bipin. So if you can just, okay. So can you discuss the compatibility of BellSoft's Java images with Kubernetes?
That's the intent,
Yes.
to give
That's,
Kubernetes compatible Java native Java images and native image kit images, which I'm going to show in a moment. So you see, yes, we can download it as a standalone tool, but of course it's more kind of cloud native to use containers for everything. Even if you don't use build packs, you can use containers with native image kit to create native images from your programs to use the exact version. You only need Docker, of course, and you will have same options with either glibc or muscle. So we provide support for muscle in GraalVM project, and we provide binaries, we provide GitHub actions, including muscle ones. So you can use Liberica native image kit on muscle systems, including Alpaca muscle. And there's a container. So at the same location here on my BellSoft's Docker Hub page, you can find Liberica native image kit container, which is a container with Alpaca and native image kit core, so-called core installed, that allows you to create native images from your Java programs, or to run them with Graal as a JIT compiler, which is not as popular as, or doesn't create as much buzz nowadays as using native images. And if you look, yeah, of course, there's a description. And if you look at the text, you will notice the same schema of naming, where tags mention base JDK version and GraalVM version, and also they allow you to choose either glibc or muscle for the images. Let's check what happens without the compilation. You see, we have downloaded the compiler inside a container during the build pack work, and it now compiles our application. It actually performs some compilation steps. It says now building universe. It will take some more time. But in the end, I'm going to show you how quickly does it start. which is our goal. Why do we spend that time ahead of time? Because we want to save our production from that CPU storm, from memory consumption storm. And we also likely will see memory savings in runtime. So the native image technology itself is also a virtual machine. So a native image is a special native executable constructed, compiled from your Java program, but it contains a specialized runtime called substrate VM. And your code is compiled ahead of time. Class information is encoded in that native executable. And it performs most of the steps available to you in traditional Java runtimes, except its dynamic features. So you must describe all your reflection before you compile your native executable. You can't load or generate code dynamically. You must provide configurations for other things like native code calls, for example. But it's possible. And a lot of that boilerplate things are already solved for you in frameworks, such as in Spring Boot. So for kind of normal type of projects, you just get the support out of the box, and you can simply use build packs, or you can create Docker files by your own. So in the end of this compilation, we will have just an executable in our target folder. We'll also have a container in our local registry, but I will show what else we can do with the native executable with the resulting binary. So for this resulting binary, we can easily construct a container image with that binary, right? The only thing that we need is to run it. In this case, we will build it on top of Alpaca muscle as a base, and we'll just copy that target binary, expose the port, and that's it. We have the working Spring Boot application. Let's try to run it. If we have it. Yeah. So I have such a container image already prepared here. So in parallel with compilation, we just start the application. So here it shows like it took almost 3 seconds, but remember that all the CPU is consumed by the compiler. And if you remember, the application took about more than 300 megabytes after it started, more than 300 megabytes of memory. So, oh, we haven't stopped the first one. No. That's the compiler, by the way. Yeah. So the second container. So here, first container is a container that performs compilation currently, and the second container is the container with the application built from the ready-made, previously prepared binary. So you see, it doesn't consume the 300 megabytes, but it consumes only 100 megabytes, 111 megabytes in this example. Let's check if it works. Yeah, it works. So we saved some resources, I hope. We haven't spent a lot of time to start the application. I will actually show you how quickly does it start after we finish all the compilation activity on this exact machine. We saved some memory because heap representation for objects in GraalVM is already optimized to have small headers. So a lot of things take less memory. We also can observe which the garbage collectors are different in native images.
Dimitri,
Yeah.
okay, so I think your screen was freezed a bit, so maybe you can for the past 1 minute or so. So if you can repeat those, it would be great. Yes.
Oh, sorry. So was it the problem with sound or
The
with
screen was
video?
freezed actually.
This
Uh,
case. I see.
okay.
Right. I was talking about native images. Yeah, probably we got out of the CPU resource. So let's start the native image. You see, it starts like in 1 second, not in 10 seconds, right? And the application works the same way. We have the same business logic, but we spend less memory because the virtual machine in the native image has a compact representation of object headers in its heap. And we, in many cases, we can get comparable peak performance with such applications. And sometimes we don't need great peak performance. We just need to have it working, right? If we have small instances and our applications are not heavy loaded, we just need them working and consume as less resources as possible. And that's the case for the native image. So I'm just, probably the CPU limited the compilation process on this host. But it basically ends up in like 6 or 8 minutes. So if we don't disturb the machine with like video calls or live streaming, etc. So we'll have the same similar container image with our application, but it will contain yeah. Let me just show you what we have here. So if it's not created by the build pack, but it's just a container image with a native executable. Oops, sorry. You see that we have it this size 200 megabytes for this native image container. So in general, we can get native images that are much smaller than traditional JDK plus application images. In case we only use a tiny subset of the overall JDK standard library functionality. If the application is more sophisticated, like in this case, the size of the container is comparable. So the static footprint will be about the same. If we compare a native image and a classical container with the JVM and the application packaged as one or several jar files. So you see it here. So like in this example, the container that has been created with a build pack based on Alpaca, it takes 173 megabytes, and this native image container is 205 megabytes. Pretty much comparable sizes, right? So we have seen some resource savings. We saw very quick instant start. And I started talking about the difference in garbage collection. So in native images, Graalvm project, its so-called community edition, the open source one, contains only CRaC. We have proposed a parallel GC implementation. It's open sourced and it's already included in Liberica native image kit. So if you create native images using Liberica native image kit, you can denote a build time flag that will enable parallel garbage collector for you, which brings better performance in terms of throughput. So you use additional cores if you have more than one CPU as the actual resource for your pod. You will benefit during GC pauses. You'll have shorter pauses, better latency, and better throughput with this garbage collector with native image. So let's get back to some startup examples, right? You see, sometimes it's complicated, right? Like it happened here. We were out of the CPU resource on the machine, and we were not able to create the resulting native image, right? So our compilation process that was performed inside the Docker container failed. But yeah, believe me, it's just in normal situation, it will succeed. But are there any other options to survive or to ease the initial storm when you start your Java applications in Kubernetes or on bare metal? Yes, there are some other technologies that are not so harmful. But again, you have to use special JDK builds for that or special base containers. So first example here is a technology called CDS. So if you remember, we have already extracted different dependency libraries from our applications as separate layers. And we can go further. We can add a step in our Docker file that actually performs some initial some part of the initialization of our classes that anyway happens on any instance that carries our application in production, and it starts working. It must perform all the class loading to initialize all the things, and then the copy of the application, the replica, is ready to accept connections, ready to actually bring some benefit to us. And this initialization step, when we load classes, it has some technical stages in it, and we can perform some stages ahead of time, and it's easier than ahead of time compilation because it's the same JVM technology. We have the same classical JVM. We have all the features of the JVM. We can have as much dynamic as we want. We can use same debuggers, same diagnostic tools, same garbage collectors. And again, frameworks help us here, and in particular in Spring Boot, the support for creating shared class data archives as a part which can be used as a part when we build our Docker images. So here we put an extra step. When we create the container, we say, please run the application. So to perform that, we must provide the environment that's, again, similar to our production environment, but it mustn't be, well, strictly similar. So it allows much more flexibility if we compare it to the native image compilation requirements. And in this environment, so here we approximately match the amount of memory in our pod with memory of the machine that we create, where we create the CDS archive. Of course, the same CPU architecture, maybe some other circumstances. The most valuable part is that we are going to keep the class path, which automatically is true when we control everything, and it's the same application in the container. And we say, please create the shared archive for us during as an additional step during the container build. And Spring has a special support for it. It says when we have finished loading context, so all the well-known great part of class loading related to the internal Spring mechanics. Please exit, so we will create a chart archive, and we will get all that class data ready for us. And it will load it much more quickly when we start the application in the real production environment, where we say, please use with this shared archive. We are going to put it, again, as an additional layer, of course, inside this container. And it happens automatically just because it's written in the Docker file. So you remember that we used, well, we can just repeat the experiment, right? You can say, please start this application for us. And you see that it starts in, see, it's balanced, 12 seconds. Okay, let's have the same power settings. And instead of that, if we have built such a Docker file with CDS support, and here it's called Clinic Advanced CDS, say, please start it for us. And now it starts in 11 seconds. Okay, probably we need to make the experiment more interesting. Say, let's use the performance power settings. Let's repeat the experiment. Okay, now it's like 13 seconds. And we skip the initialization part. And we will see that the CPU consumption will be less because we won't spend, and you see, 10 seconds instead of 13. That's not a kind of saving when we start in 1 second instead of 10 that we have seen with native images, right? But that's a significant saving during our start period, right? Especially if we have a lot of libraries, if we initialize a lot of beans, all the things, all the context is ready for us. So we're just finished. And we spent slightly less memory after the startup because, again, we don't consume native memory for the process of constructing class data. So we have skipped this part. Again, required mostly nothing from the development side, right? It's the setting for the application setting for our CI process where we build the container. Probably an easy thing to do. What's the price? Sometimes there may be an incompatibility, of course. I already mentioned that. That's, I would say, a rare case, especially if your build and production environment is more or less unified. But when we look at the images that we have, you will see that the CDS image static footprint is larger. It's noticeably larger because we actually save a copy of a part of our application memory on disk, and for all the subsequent usages, we just memory map it. But you see, when we need to update our application, update our container, we will transfer more data just because of this shared archive that occupies that disk space or that network bandwidth. Well, what about other options? Can we start as fast or almost as fast as native image and still keep the advantages of the classical JVM? Yes, we can. So for that CDS example, I've used a special base CDS image that can also be found on the Docker Hub. So we need the JDK that already contains the CDS archive. So we use a JDK container that already contains the so-called standard JDK CDS archive in it. And we later build an image that contains the application archive, and only with such combination it works perfectly. So that's an important part here to use that CDS image. And that's configurable in the same way. We just use text and we get the image. So it's a normal JDK. And if you have downloaded some JDK version, you can create the standard CDS archive inside the JDK, just saying something like java share dump. So it will dump the archive. So if you download the JDK without CDS archive, or you have a special environment, you can do it. You can create the container image that contains a proper CDS archive, standard CDS archive for your JDK classes, or for whatever purposes that you can imagine. Okay, what about the more advanced option when we start really fast and when we still keep the traditional JVM? Well, it's called the CRaC JDK. So there's a project, the OpenJDK project called CRaC, coordinated restore at checkpoint. It's an abstract, the kind of abstract API and description, and the implementation is currently based on a CRaC project in Linux, checkpoint and restoring user space. So we are able to freeze a copy of one running instance and restore it to as many copies as we wish. Of course, it has its downsides. We must be aware of any consequences of having the copy of the same thing in multiple places. Like any For example, if you have a global unique identifier, it, it no longer stays unique. So there are hooks that you can use to reset all such places, and that's performed for standard, important standard JDK standard library internals, such as secure random. So we'll have different secure randoms on both copies. So if we download the JDK, there's an option to download CRaC JDK. Okay, I'll probably, yeah, all versions. And there's a, you see, CRaC JDK. So CRaC JDKs are available for JDK 17 and JDK 21 as a different flavor of Liberica. And of course, they are available as containers. So if you look at Liberica runtime container, you can search for CRaC, checkpoint and restore, and you'll see all the text filtered. So you see you can combine CRaC and CDS, and you can use that technology with glibc or with muscle. Just take an appropriate JDK. So on top of that CDS exercises, we are going to say, please create a checkpoint for us. But it's not that simple. We are going to start the application, and we are going to say, hey, when we run this container, resulting container, please create a checkpoint. So when we start the resulting container from this, derived from this Docker file, this container will create the checkpoint, and it will happen automatically, and the application will end the execution because Spring Boot has support for CRaC technology. So at the same point where we start loading all that mass on the application startup, we'll create the checkpoint, and we will put the checkpoint on a separate layer. But to run this container, to create checkpoints, to restore checkpoints, we need special permissions. So Creo technology requires special permissions to invoke all the necessary kernel stuff that actually helps to create snapshots of processes. So we need caps. And if we create that containers with caps, there are basically two ways of doing things. First, we can still try to keep one Docker file that will perform all the steps. But running something with extra permissions during build requires us, well, to create a special builder, to use buildx process. And I would say it's not yet too friendly to any errors that can happen. So I would recommend, instead of that, I would recommend the second way. To have a tiny script that actually creates first creates and runs the container, and after that to change the entry point. So we can try to reproduce the build, right? So we have that advanced CRaC Docker file, and we say, please build the container for us. So let's see what happens. So we've got the image, and we run and we create it. So we have created the container that does the checkpoint. Then we are going to run this image. And we add that extra capabilities. And we must reproduce again the production environment as close as possible here, at least in terms of how it looks from the inside of the container. Let me see. We have some nice things here. And after that, we commit that container. After it has created the checkpoint, we commit that checkpoint as an additional layer, and we finally get the resulting container where we change the entry point, and we say, please run starting from the checkpoint. And only after that we can remove that helping container. And to run that resulting container that contains the checkpoint, again, we need that restore capabilities, right? So you can say, please run, please run the resulting container. Oh. Oops. Let's remove it. Start properly. Yeah. You see, we have started in a half of a second. So we can go back to the application, check does it work. So we just proceed from the same place. And we skipped all that storm. Let's again try to catch what happens here. You see, no extra CPU usage, and the memory usage is quite small because we don't need to allocate all that service memory that we have allocated in our training run, right? The run where we captured this snapshot. And we can even try to put some load on the application before we checkpoint it. So we will have optimized peak performance code that can be replicated to all the replicas of our application. That gives us faster scalability, that gives us more predictable scalability because we have close to peak performance from start. And we save a lot of time because some applications, even like microservices, can take an hour to warm up to reach their peak performance. And during that, we have strange metrics observed from instances that actually only begin to live their life. So you see, we can have that instant starts from native image, faster start from CDS, and again, almost instant start from CRaC. And by the way, we don't have to rely only on the framework support. So here, the moment where the checkpoint happens is controlled by the framework, right? So we see please checkpoint on refresh or please exit on refresh. And we can invoke the checkpoint manually from the inside of the container or from our host or from a service container just by using the J command interface. So we just need to invoke the JDK checkpoint command. and it will create that checkpoint inside our running container. All right, that's. I think all that technologies help our cloud deployments in different ways. We have kind of choice here how complex we are ready. So we can trade complexity for the results that we can get. So probably native image is the most complex technology because it requires a lot of configuration. It has limitations in runtime, sometimes performance limitations. But the start, we get big performance from the start. CRaC is balanced, but of course we must provide and use special capabilities. CDS doesn't require any extra capabilities, but it doesn't provide you as fast startup as two others. So that are advanced technologies for to create your containers from your Java applications. And remember that you can create native images using build packs, which is much easier from the configuration point of view. Right. Ready to answer questions if there are any.
So I think the question I asked, that was the question we have by now. So like as a sum up or summary, like if I just highlight this one, okay, I was just talking about this, the compatibility of BellSoft. So I think you can just now summarize that one, I guess. Are you done with
Uh,
that?
yeah, so for Kubernetes, you of course provide not just your container images, but also you have requirements to run that container images. And as I mentioned, the images created using CRaC technology require capabilities that you can enable using Kubernetes, right? And all that Java images are KDS compatible. They are targeted to save your resources, to save in the cloud.
I don't think we have any other questions from the folks. Yeah, nothing. Yes. So, any other thing I would like you want to add? Like, is there any ways to get involved into these things?
Yes, please check our blog. I'll try to share the screen
Uh,
again. So
oh, and
you can
so like,
find it here. Just the blog. Um, and there are articles related and most of the articles are related to using your Java applications in Kubernetes in cloud environments. And probably you can find more answers right there in the blog. And it explains how to use CDS, how to use CRaC, how to use native images, and how to create them.
okay, great. So yeah, folks, you can just go to the link, or you can also, Dimitri, you can also share the link with me. That would be also great for so that I can share with the folks, right? Maybe you can
Yeah.
share in the chat or give in the private chat. So you can do that as well,
Yeah.
so that folks can go and check that out.
I'll try to. It should
Thank you.
be.
Oh, okay. Share this request.
There's the last slide. I think
Oh,
that's the easiest way to get it.
okay.
Oops. So
Oh,
that's the presentation by some reason.
I think you were talking
I'll
about the
share the last
scanning
slide.
part, right?
Yeah, yeah,
Yes.
that's a scannable
So
code.
Yeah, folks, again, and now scan from here, and as it is a live stream, and it will be obviously uh, there out there in the YouTube and LinkedIn after the session as well, so you can just check that out if you are interested on that. So yeah, so I think that should be good. That should be good for us. Yes, they can check that out later on. So yeah, thank you so much, Dimitri, for an awesome session and for your awesome time.
Thanks, Metal. Uh, yeah, see you next time.
Yes, sure.
Welcome.
Okay, so bye, Dimitri. So, okay.
Bye bye.
Okay, so let's close this down. So thanks everyone for joining the latest episode of Cloud Native Live. So enjoy the interaction and questions from the audience, and thanks for joining us today. And we hope to see you again